President Perez, and excuse me, President Perez, distinguished guests, it's great to be here. President Perez, you and I spoke in a joint keynote in 1985 in Tel Aviv at a technology conference, and you gave an eloquent address where you talked about how technologies were emerging that would transcend national boundaries. So how has that worked out? Well, today we have missiles that transcend national boundaries, biological viruses transcend national boundaries. The internet covers the whole world. We have $2 trillion of e-commerce on the internet. The founder of Google and I did for the National Academy of Engineering in the United States, where we looked at all the different emerging energy technologies and selected solar as being the most promising because it's growing at an exponential pace. It's doubling. The total amount of solar energy we're creating is doubling every 2 years and has been for 20 years. But people don't notice exponential growth because you start out doubling tiny numbers. But it has doubled 10 times already. It's only 8 doublings away from meeting 100% of the world's energy needs. Well, then the Prime Minister asked, do we really have enough sunlight to do that, to keep doubling another 8 times? And I said, we have 10,000 times more than we need. We only have to capture 1 part in 10,000 of the sunlight that falls on the Earth to meet all of our energy needs. And we're applying nanotechnology, which is a form of information technology, to create new materials and new solar panels, new energy storage devices, batteries, that are growing at this exponential pace. That will keep this going for a very long time. And within 16 years, 8 more doublings, we can meet all of the world's energy needs. And he thought this was very intriguing and announced yesterday a national commission to really accelerate this process. But people tend to dismiss exponential progressions when they're at a small stage. The Genome Project was announced in 1990. Mainstream scientists said, there's no way you're going to sequence the entire human genome in 15 years. We've just had our best scientists and most advanced equipment, and around the world we collected 1/10,000th of the genome in 1989. Halfway through the project, the skeptics were going strong, saying, I told you this wasn't going to work. Here you are halfway through the project and you've only finished 1% of the project, kind of where solar energy is today. But that was right on schedule for an exponential progression. It had been doubling every year, but you start out doubling little numbers. By the time you get to 1%, you're only 7 doublings away from 100%. It continued to double every year. The cost came down by half every year. It was $10 per base pair in 1990. It's a small fraction of a penny today. The project was done a year ahead of schedule. And every other aspect of biological technologies are gearing up at this exponential manner, and Israeli technologies are in the lead in many of these areas. When Bibi and I were students at MIT some decades ago, we all shared a computer, took up half a building, cost tens of millions of dollars. The computer in my cell phone today is 1 million times cheaper, it's 1 million times smaller, it's 1,000 times more powerful than the computer Bibi and I shared some decades ago. That's a billion-fold increase in the amount of computation per shekel, per dollar, as of a few years ago. We'll do that again in 25 years. As powerful as these devices are already, we'll multiply them another billion-fold in the next 25 years. And what used to fit in the building now fits in my pocket. What fits in my pocket today will fit inside a blood cell 25 years ago. We're going to be putting these intelligent computers inside our bodies and brains. If that sounds very futuristic, I'd point out that we're already doing that. If you're a Parkinson's patient, you can put a computer inside your brain today. Some of this technology has been pioneered here in Israel. It actually replaces the biological neurons destroyed by that disease. The latest generation actually allows you to download new software to the computer inside your brain from outside the patient. It's not blood cell size today, it's pea-sized, but we're going to shrink that 100,000-fold over the next 25 years, so these will be the size of a blood cell in 25 years. Now, it was mentioned earlier that you can't predict the future. That's true if you talk about when a war is going to break out, which company is going to be successful. But if you talk about the underlying power of these technologies, the number of MIPS you can buy for $1 of computation, number of bits per dollar, number of bits we're moving around on the internet, the number of bits of data we're getting about the brain, the spatial resolution of brain scanning, the power of biological technologies. I could mention 50 other things that are basically measuring the power of information technology, not just with these electronic gadgets, but in many different fields. They follow very predictable trajectories. I started studying this 30 years ago because I realized that timing was successful to being an inventor, and I wanted to see if I could predict where technologies would be so that I could meet that moving train, because the key to being successful is timing. Larry Page and Sergey Brin had a great idea about search engines, but they did it at exactly the right time. So I began to study technology trends. I looked at many different technologies, and I wasn't expecting to see a ready formula that would predict it, but I thought maybe we could get some idea of where technology would be. And I made a rather startling discovery. If you look at these underlying measures of the power of information technology, they follow exquisitely predictable trajectories. In the case of computers, this goes back 120 years to the 1890 American census. Very smooth exponential growth, doubling every few years. Now it's doubling every 11 months. That describes the trajectory of these technologies. And what we can predict is that they grow exponentially, and that's not intuitive. Our intuition is that technology, or that everything, progresses in a linear manner. If I take but there's a profound difference between our intuitive linear perspective and the historically correct exponential perspective. If I take 30 steps linearly, 1, 2, 3, 4, 5, and that reflects our intuition about technology, I get to 30. If I take 30 steps exponentially, 2, 4, 8, 16, and that reflects the reality of this progress, I get to 1 billion. It makes a huge difference. That's why my predictions about these technologies are surprising to people. In the early 1980s, I saw the predecessor to the internet. It was called the ARPANET, after the U.S. Defense ARPA agency, doubling every year. But it was only tying together a few thousand scientists. But I did the math and projected a World Wide Web connecting hundreds of millions of people to each other and vast knowledge resources emerging in the mid-1990s. People thought that was ridiculous when the entire American defense budget could only tie together 2,000 scientists in a year. But it happened right on schedule. That's the power of exponential growth. Doubling every year means multiplying by 1,000 in 10 years, 1 million in 20 years. And it's not just these gadgets we carry around. It affects everything we care about. And an important area is health and medicine. Health and medicine was not an information technology up until just recently. It was hit or miss. We would just find things that happened to work, but we really didn't understand why they worked. Now, it is an information technology. We have the human genome, which I mentioned. That was an exponential progression. That represents the software that life is based on. Now, how long do you go without updating the software on your cell phone? It updates itself every few days. But we have software running in our body, our genes, that are thousands of years old, some cases millions of years old. One example, the fat insulin receptor gene, says hold on to every calorie because the next hunting season may not work out so well. That was a good idea 1,000 years ago. We had no refrigerators. We stored our food in our bodies. Today, that underlies an epidemic of obesity, especially in my country. Well, we'd like to be able to tell the fat insulin receptor gene, don't store every calorie. We'll have enough calories tomorrow. That was actually tried. We have technologies that can do that in animal experiments near where I work in Boston, Massachusetts.